Now we're going to continue with our study of waves by now talking about light waves. So for a very long time, there was a lot of controversy going back and forth about whether or not light was a particle or a wave. And based on experimentation, we've realized that it actually is a little bit of both. But in this unit, we're going to specifically talk about light's wave properties and how it demonstrates those properties. So if we remember the wave equation, remember that velocity is equal to wavelength times frequency. So we can apply this wave equation to light as well, where f is the frequency and this is the wavelength, and that's equal to the letter c. C is the letter that's given for the speed of light in a vacuum, which is a known value, and I'll talk about that in a second. So what are light waves? Light waves are actually electromagnetic waves, and they're actually oscillating electric and magnetic fields. And so you can see that they're transverse waves here. Right? They're also known as radiation. So they transfer energy through these electromagnetic waves. But it's important to note that they are different than mechanical waves because mechanical waves require a medium to travel through. So they've got to be in liquid or in a solid or in air, whereas radiation or electromagnetic waves, light waves, do not require medium. They can move through the vacuum of space. Now we know that all electromagnetic waves move at the same speed in a vacuum, and they also move about that same speed in air. So in general, we use the speed of light as 3 times 10 to the 8th meters per second. This value is given on your reference tables and will be used for the velocity of light unless it's traveling through a more dense substance like glass, and we'll talk about later what happens when light travels through mediums like that. Now, visible light is only a very small range of electromagnetic waves, and they have a wavelength somewhere between 400 and 700 nanometers. That's 4 times 10 to the negative 7th to 7 times 10 to the negative 7th meters. And based on the wavelength determines what color that you actually are. So reds fall somewhere between the 600-700 range, whereas blues are and violets are on the other end of the spectrum, closer to 400 nanometers. Now, there are electromagnetic waves that fall outside of the visible range. The visible range is really only a small part, and those make up the entire electromagnetic spectrum. So electromagnetic waves can range from waves that are really, really large, like radio waves, to very, very tiny, like gamma rays that can actually penetrate into your tissues and do like damage to your DNA. Okay, so dependent on your wavelength determines what kind of electromagnetic wave that you are. Typically, waves that are on the left-hand side are helpful. Microwaves, infrared, radio waves. These things actually do not cause harm. They're not dangerous to us. They're too large and they don't carry enough energy to really harm us at all. Whereas on the other end of the spectrum, we do have uses for these things, but they have the potential to be harmful because they are so high energy, and when they come in contact with our tissues, they can do damage. So like UV rays can cause skin cancer. X-rays, when you go to the doctor and you get an X-ray, you have to wear like a lead blanket in order to prevent being overexposed to X-rays. Gamma rays are the types of radiation that are produced by atomic bombs or nuclear spills and things like that, so they can be potentially harmful. So when we're talking about light waves or radiation, it includes really the entire spectrum, and they all have that same speed. All right, so in the next video, I'll continue talking about light waves and waves properties in particular.